I remind you that we are in the middle of the canonical ensemble representation. Okay. Last week, what we managed to prove is that if we have a bunch of independent particles, right, and we have used the canonical ensemble in order to derive the partition function for those particles, right, the factorization allows us to treat each and single particle as if it was a big system. Okay? So if we have independent particles, we have shown, okay, first of all, that Z is a pi over I of Z of I. Okay? So we need to calculate the partition function for each particle, multiply all of them together, right? And this is how we obtain the partition function of the total system, right? To find a system in a specific state I was e to the minus beta ei divided by Z, the partition function. Okay? Ei is the energy of state I, Z is the total partition function. Now what we have managed to show is that if we look on f of I and j, okay, so what is the probability of particle number I, okay, of particle number I to be in state j? Okay? So those probabilities behave exactly as if particle number I was completely independent of everybody else and as if it was a big system on its own, right? Remember, we developed the statistical mechanics representation using heat bath, using a notion that we have a big system. It was a macroscopical limit, a lot of different particles. But eventually, due to the factorization, what we know that each and single particle, as long as they are independent, behave in the same fashion as if it was a system on its own. So this Fij's simply e to the minus beta epsilon ij divided by zi. Okay? The only thing that I need to know is the partition function I of this particle and the exact energy of the state that I'm interested to calculate the probability of this state. Right? Now this is actually very helpful. How it's helpful? Because we can look on different systems, right? And if we manage to look on this system, any system, as a sum of independent particles, right? The only thing that needed to be calculated is the partition function of one single particle. That's it. The moment we know this, we can calculate everything else. We can calculate the probability of this particle. And from the probability of a single particle to be in a specific state, we can march forward towards probabilities of different other states. We'll see this again in the example of the polymer model. Okay. So we already solved the two-state model, the Einstein model, and the third simple model that we used in the microcanonical ensemble was the polymer model. I will remind you what exactly it is. So we have a wall. Okay. We have a polymer that is constructed of a sum of monomers. Okay. Okay, so we can continue this. Okay. We can have a pulley at the end of this of this final state. There is a pulley, and we pull with the force tau, okay, on the end of this pulley. Yes. Questions? No? So this is our polymer. A lot of monomers connected somehow to each other. We're pulling on one side of this long polymer. Okay. and we calculated using the microscopical ensemble different probabilities. And you remember it was a combinatorial nightmare. We had nx, the total number nx plus, so let's do it slowly. N is the total number of monomers that we have in a system. Is the number of monomers that we have. We also had nx plus, okay, so those are the monomers that are oriented in the positive direction. We had nx minus, the number of monomers that were oriented in the negative direction. Okay, so this guy is oriented in the negative direction, this guy is oriented in the positive direction. We had ny plus, it is the monomer that was oriented in the positive y direction, so this guy over here. Okay, and we also had ny minus. Okay, so ny minus was this guy, for example. All we know that n, the total number of monomers, is nx, ny, nx plus, nx minus, ny plus, ny minus. This was a constraint. Additional constraint was the total length of the monomer. Okay, the total length of the monomer was nx in the x direction, nx plus minus nx minus, multiplied by a, let's call the size of the monomer a. Okay, the y direction was what? Ly, okay, ny plus minus ny minus. An additional constraint was the energetic constraint. The energetic constraint came from the fact that we have an epsilon, right, energy if a monomer is perpendicular to the x direction, perpendicular to the direction of the force that is applied on the polymer. Okay, we had an additional energy epsilon, and a zero energy, right, zero energy if it's parallel to the x-axis, right? So the total energy was constant, U. So we had four constraints, and we had this combinatorial form. We needed to satisfy all those constraints. We needed to use the Stirling approximation. It was really, really wrong and really, really awful. Okay? So now we're going to solve it in a much more nicer way. Okay? So what do we know and what we claim? First of all, we need to use still some constraints. So the constraint that we use is, well, the length of the monomer, the polymer, is still nx plus minus nx minus multiplied by a. So nothing wrong here, still the same. If I want to calculate the total length, it is still Lx. And it's still I count the total monomers that go in the right direction minus the number of monomers that go in the negative direction. I can also calculate what? I can calculate the energy. So what is the energy? The total energy, U. Okay. So we remember there was an additional energy, as I mentioned, to every monomer that is perpendicular to the x direction. So we have ny plus ny minus multiplied by epsilon. Okay. But here we also have an additional energy. What is the additional energy? We pull on this guy, okay, with some force tau. So the energy of this pulling is some constant, let's call it C tilde, minus tau Lx. Okay? So you can assume that I'm putting a weight, okay, of a magnitude of tau divided by g, right? And this weight is pulling down, okay, on this polymer. Now the energy that is associated with this weight, okay, is the extension of the total polymer minus some initial length that according to this length I start to measure everything. Okay, instead of doing this, you can assume, well, let's write it down as minus tau L x minus some L0. Okay? So because I'm pulling the energy, it depends also on the extension. So this is my total energy right now. This is all I know, and I want to use canonical ensemble or canonical representation in order to solve this. So something else I need to tell you that there is a temperature, and T is the temperature. Okay, so the whole idea behind canonical ensemble or any problem in statistical physics, and one can say in physical in general, is to say, I have a problem, I have a bunch of particles. Okay? The only thing that I can solve is the case where those particles are independent. So somehow, they're already independent here, somehow I need to use this idea of independence of all those different particles, okay, and describe my partition function as a sum of all different independent particles that I have in my system. Okay, so what we see over here, let's look on the energy. Okay, first of all, we know that all the different monomers are independent of each other. The only thing that I need to show you is how I write the energy as a sum of the energies of all the different monomers that I have in my system. Okay? So instead of Lx minus L0 over here, I can write that U equals Nx plus Nx plus Ny multiplied by epsilon minus tau multiplied by this guy Nx plus minus Nx minus multiplied by A, and also I have here an additional constant tau L0. I completely don't care about it, it's a constant. Energy is always defined up to some specific constant, and this is my constant over here. I can simply erase it. I don't care about it. Okay? Now, let's look on the form that we have on the board over here. Okay? So the board over here says that the total energy is this guy multiplied by epsilon minus, and write the A over here, minus tau A, Nx minus Nx plus minus, no, here it is Ny. Ny plus, Ny minus. Okay? So I'm saying the following thing. This energy over here, I'm summing up over all different monomers that I have in the system. Each monomer can have different energies. Okay? If the monomer is in position up, the energy of this monomer is epsilon. If a monomer is in position down, the energy of the system is epsilon. If the monomer is in position oriented towards the right, the energy of this monomer, according to this formula, okay, we'll write it down as minus tau A. And if the monomer is directed to the left, the energy of this monomer is plus tau A. Now, this I summed up over all different monomers in my system, okay? And I'm following this summation. For each monomer, I'm saying, well, if the monomer is in, it can be either up, down, to the right, or to the left, okay? So when I sum over everybody, the total number of the monomers that is oriented to the top is Ny plus, and the energies of all those monomers is Ny is epsilon for each one of them. Okay, so it's Ny plus multiplied by epsilon. The same thing goes, okay, for all the monomers that are oriented downwards. Okay, the energy of each and every one of them is epsilon. So the contribution to the total energy is Ny minus multiplied by epsilon. Okay, part of the monomers are oriented to the right. So the total energy of each of them is minus tau A. Their total number, it's nx plus. Okay, so they contribute to the total energy, okay, minus tau A. And I still left with the monomers that are oriented to the left. The total number of them is nx minus, and the energy of each one of them is tau A, so they contribute to the total energy nx minus multiplied by tau A. So I can may say the following: U of I, so the energy of monomer number I, is one of the following. It's epsilon minus tau A plus tau A, and it depends on the orientation, okay, of this monomer. And the total energy, if I defined Ui in the following fashion, the total energy is a sum, I goes from 1 till n, of Ui. Okay. So what we achieved by doing so, we know that all the monomers are independent, and we know that the total energy is simply a sum over all the energies of all the different monomers. The moment I have done it, and I'm saying I'm using the canonical ensemble, the factorization applies, and the only thing that I need B, they're all identical, meaning that the partition function is simply a power n of a partition function of one single monomer. So the only thing that is left is to compute the partition function of a single monomer. Okay? Z is Z1 to the power n, okay, and Z1 is what? E to the power minus beta epsilon plus e to the power minus beta epsilon. This guy is contribution if the monomer is oriented up. This guy is a contribution if the monomer is oriented down, plus e minus beta minus tau A. This is a contribution if the monomer is oriented to the right, plus e to the minus beta tau A. This is a contribution if the monomer is oriented to the left. That's it. This is all we have, and the partition function z is simply a power n of e to the minus beta epsilon multiplied by 2 plus e to the power beta tau A plus e to the power minus beta tau A, all of this to the power n. Okay. I want to compute the free energy. I can, is minus 1 over beta log of z. I want to compute the specific heat. I take the derivative of the free energy with respect to temperature. I want to compute the energy. Okay, I have a formula for computation of an energy, but I can do either also something much more simpler. Okay, if I want to compute what is the probability of average Lx, what is the average length of my monomer? Okay, so remember, we computed the compressibility by calculating how this quantity over here behaves if I take a derivative of this guy with respect to temperature. Okay, so, or with respect to the force, tau. So what is Lx average? Well, I have n independent particles, right? They are completely independent. So Lx average is simply the number of all my different particles multiplied by Lx average. What is this? The average length of the monomer. Right? I have n independent random variables, Okay? I want to compute the total length is the sum of all the different monomers. If they are in position which is oriented parallel or anti-parallel to the y-axis, okay, they do not contribute anything. The only thing that matters to Lx is either a monomer is in the right orientation or in the left orientation. Okay, so what is this guy over here? What is Lx average? Lx average, okay, is the probability P of a monomer to be in positive orientation, so the probability of a monomer to be of length A multiplied by the value, which is A, plus the probability of the monomer to be in state minus A, so be negatively oriented, multiplied by the value minus A. Okay. Now, what is this probability over here? So it is the probability of a single monomer to be oriented in the x direction. We know that we can treat all the system or each of the particles as if it was independent of everybody else and treat it in a statistical mechanics fashion. Meaning, we only need to take the Gibbs factor and divide everything by Z1. Okay? So this guy is e to the minus or plus beta tau A divided by Z1. What is Z1? Is this guy over here. 2 epsilon minus beta epsilon plus e to the beta tau A plus e minus beta tau A multiplied by A. Okay, this is the A over here, plus the probability of the particle to be oriented in the minus direction, okay, which is e to the power minus beta tau A divided by 2e minus beta epsilon plus e beta tau A plus e minus beta tau A, okay, multiplied by minus A. And this is all. Because this is the average length on the x-axis of each single monomer. They're independent of each other. Okay? Now, what is the total sum of n different monomers independent or average? The average is the number of variables that we have, n, multiplied by the average of each and single one of them. Okay? This is the formula that is written over here. So we know that Lx average is NA. Here we have e to the power beta tau A plus e minus beta tau A divided by 2 epsilon minus beta epsilon plus e to the power beta tau A plus e to the power minus beta tau A. Where? Minus, yes, thank you. This is minus. Okay? So we can even dress it up a little bit more. So it's Lx average. This is, you see, this is a hyperbolic sinus, right? Up to a prefactor of 1/2. And this is a cosine, right? A hyperbolic cosine. So this guy is 2NA sin beta tau A divided by 2 epsilon minus beta epsilon plus 2 cos of beta tau A. And we can actually get rid of the 2's. And this is the formula. We want to take derivative of this guy with respect to t, we can. We can want to take derivative of this guy with respect to tau, the strength that we are applying, we also can. Now this way is much more easier than what we've done before. Try to compare. We do not use Stirling approximation. We don't have obscure combinatorial prefactors, etc., etc., etc. It's really easy. The only thing that is difficult is this step. You need to go in and try and find your way how you represent the system as a sum of energies of different particles. The moment you have done it, you've solved the system. Okay? Because you started from the point that all the particles are independent, and you need to satisfy the other condition, which is that the total energy is a sum of all the different energies of single particles. Okay? Now this is what we are going to try and perform for many other systems. Okay? The trick will be, or the problem usually will be that we won't start from a situation where everything is independent. Usually we will start from a situation when all of those particles are somehow dependent, and we will need to find a transformation or a nice way to look on the system such that they all become independent. This is basically the only thing that physics eventually can do. They can still solve very simple problems, and most of our time we try and represent complex problems in terms of very simple ones. So this is it about the canonical representation. What we are going to do now, today and tomorrow, is we are going to solve additional model, which is much more realistic, and this is called a Debye model. So remember, the Einstein model was the model to describing the behavior of a solid. We have a lot of different atoms inside, and the simplest assumption made by Einstein is that all the different atoms behave as regular oscillators, which are completely independent of each other. And we have shown that it's definitely not true, because the heat capacity at the low temperatures was behaving differently from what is observed from experiments. It works extremely well when the temperature is high, because then everything oscillates and they don't care about each other, all those atoms. But at the very small temperatures, low temperatures, okay, what happens is that if you take an atom and an atom nearby, they do not do something like this. They do care about each other. They prefer to oscillate together. And this specific feature is missing in the Einstein model. Okay. Basically what we are saying, that all those 3n atoms, or all the different atoms inside a solid, are correlated. They are not independent. Okay. So even if we will try to apply the canonical ensemble representation, we are in a problem. What is this problem? The problem is that we are treating a lot of different atoms, that their motions are correlated. Okay? So the attempt of Debye to solve this is actually to say, yes, I'm starting from a system where everything is correlated. How can I eventually achieve something like this? Something that have a lot of different particles, independent particles, okay, and that the total energy of the system is the sum of all the energies of all those different particles. Okay? We will see that we start with atoms, but eventually we will end up with something that is named quasi-particles. The quasi-particles are not exactly particles, they are something else. Okay? But still, this is the way to go. But before telling you all about the Debye model, don't worry, we'll do it, or it is started, I want to tell you a little bit of a situation when the energies are not discrete. Right? So what do we know? We know from quantum mechanics that the spectrum, energetic spectrum of any problem, depends on the Hamiltonian. Okay? Now, if you remember, you have this Schrodinger equation. You work really hard to solve it. We know how to solve it like for 10 models, but doesn't matter. We work extremely hard, and eventually we obtain, due to the boundary conditions, right? What we obtain? We obtain that there are sometimes discrete set of energies for any given system, and sometimes the energies are continuous, right? So for example, particle in an infinite box had a discrete set of energies. Oscillator has a discrete set of energies. Free particle in quantum mechanics, okay, has a continuous set of energies. Okay? There is no gap. Right? How can we do our statistical physics for systems where the energies are not discrete? Okay? So what we do, we count, right? Over here. in order to find Z, we counted all the different states. What we are going to do if we have continuous set of energies? Instead of doing sum, what we are going to do? An integral, right? So this is very easy. Exactly as if you have been taught regular mechanics. Okay? So you have a set of masses, and then you say, well, I have this block, and how I calculate the total mass of this block, I integrate over the density. So in the cases where we do not have discrete energies, but we have continuous energies, we are talking about density of states. Simply DOS. Okay? The idea is extremely simple. If this is my energetic spectrum, okay, the usual picture is that I have a lot of different energies. This is my energy. And those are my eigenstates. E1, E2, etc., etc., etc. So when I calculate the average value of observable O is my observable, according to the canonical representation, is a sum over all different states of the system. The value of my observable at this point, for example, the energy, at this specific state, multiplied by e to the minus beta e I, all of this divided by z. Okay? This is the perspective that we have seen so far. What happens if my energetic spectrum E, right, is already, as I told you, not discrete, but it's continuous, okay? It's already continuous function. We need to tell each other, at least, what is the density of state for a given delta E. Okay, so if we have a delta E, and this delta E is small enough, d of E multiplied by delta E is the number of states in an interval delta E. Okay? Think about the mass. Okay? If I have a lot of small masses, I just count all of them. If I have a mass which is continuous, I'm saying, well, I need to talk to you about the density of mass, right? And the density of mass multiplied by the length of the object, if it's one-dimensional, is the total mass. Exactly the same. The number of states over here is delta dE multiplied by delta E. Now, if I'm looking again on this observable over here, so what I need to do, I'm saying for this specific case, the average O is, instead of having an integral, I will have this prefactor, yes, I will have 1 over z. But it's an integral over all the energies, okay? O of energy E, E minus beta E, okay, dE, dE. Fine? No? What's Malaya?
What's something to replace this z function with
1 over z. I have a 1 over z. Right, so z here was a sum, right? What is z over here? Z is a sum over I, E minus beta EI. What is z over here is going to be? An integral, right? An integral over E minus beta EI, etc., etc. If we need it. We will see that sometimes can be a little bit different, but let's leave it like that. So if we know that we have a system where the energies are continuous, so instead of doing summations, we're going to do integrals. Now, what kind of system do you know but their energies are continuous. So I mentioned, right? I mentioned free particle in quantum mechanics. Now in quantum mechanics, the free particle is not exactly a particle. It's described by waves, right? When a solution of the Schrödinger equation is wave-like solution of sines and cosines, right? And I sum or integrate over all of them. So for any system that is represented by waves, the representation of the energies is going to be continuous. So what we are going to find now is, well, yes, this is an easy way to do. This is an easy thing to do the moment you know dE. The moment you know your density of states. But how you find your density of states, right? It's easy to write this down. There's still a question, what is dE? Okay? So we are going to find the density of states for the case where the system is composed out of waves. Okay? So for a system that is described by a lot of different waves, right? Galim, what is the density of system for such case? Now we're not talking about general waves, we're going to talk about standing waves, right? So I'll formulate the problem. I want to find the density of states of a system that is composed of waves, and I know that those waves all together live in a box, okay, of L by L by L, okay? And all those waves, the only waves that are surviving in this box are standing waves. Okay? Now, how do we start? First of all, we know that the energy is h bar omega. Okay? This is we know if we have a wave. Okay? And also we know that there is something that we term a wave vector, right? So we have P, which is a momentum, is h bar multiplied by k. Now we're going to relate this k to omega, okay? And obtain by exploring the behavior of this k, etc., etc., we are going eventually to obtain this density of states. So we are treating standing waves. Okay. What is k? If we had only one-dimensional system, and this length is L, the wave vector is simply defined as 2 pi divided by lambda. What is lambda? Lambda is the wavelength of my wave. Okay. Now I know that I want to treat only standing waves, right? Standing waves means that the total number of half length of the wavelength is an integer number. So L divided by lambda over 2 equals to what? Equals to n. Okay? Which basically says that the lambda, or all the wavelength that I have in my system, is simply 2L divided by n. Now k equals to 2 pi divided by lambda. So we know that k is what? K is n pi divided by L. Okay? So for any one-dimensional system, the wave vector, one specific dimension, if I have a standing wave, is related to the size of this dimension by this formula over here. Okay? And this is how discretization is coming inside. N can be what? 1, 2, 3, 4, etc., etc., etc. Okay? N is an integer. Now, my general wave vector have 3 dimensions. I'm looking on a system that is living inside this box over here. So k in generally is kx, ky, and kz. Right? I have a 3-dimensional vector. If I had a 4-dimensional box, I would have a 4-dimensional vector. Okay. Now kx as n multiplied by pi divided by L. The same is for ky, the same is for kz, but this number n over here, it is different for each dimension, right? Because I can have 2 waves or 2 half waves in the x dimension, 1 half wave in the y dimension, and 3 half waves in the z direction. Okay, so I have here pi nx divided by L, pi ny divided by L, and pi nz divided by L. Again, can get out of this vector the pi divided by L, so it's pi divided by L, nx, ny, and nz, right? Let's go up. And I want to generalize it a little bit more by saying, well, L, okay, is the size of each of the corners. But I don't want to use L, I want to use the volume of my box. So I'm simply saying that this is pi divided by the volume to the power 1/3 over nx, ny, and nz. What's the next step? So this is k. This is vector k. What is going to be the next step? Next step, we are going to say, well, let's look on this vector over here, nx, ny, and nz, right? So the vector nx, ny, and nz equals to v to the power 1/3 divided by pi multiplied by k. The size of the vector on the left, nx squared plus ny squared plus nz squared to the power 1/2 equals to the volume to the power 1/3 divided by pi by the size of the vector k. Okay? Nothing really bad happened so far. Okay? But I want to calculate density of states, DOS. So what is density of states? How we calculated so far, some densities. We can calculate the total number of states, right? And then take the derivative with respect to some parameter. Okay? So this is exactly what we are going to do over here. Okay? We want to calculate, remember, the energy is provided to us by this relation, EH bar omega. If we know omega, we know the energy. We want to calculate the density of states for a given energy, but it's equivalent to calculate the density of states for a given frequency, omega, right? Now, I know that there should be some sort of a dispersion relation of k omega, okay? So how my wave vector depends on the frequency of the waves.
E equals p squared over 20?
No, not exactly. This is for one specific media. There are different kind of medias. It depends on the media that I'm looking on. Okay? So only for an elastic, some sort of an elastic media, your relation will be right. But in general, I don't really know what k of omega is. I don't really know. Somebody should tell me that, okay? If it's an elastic media and it's a model, I can calculate it. If it's experimental system, okay, I should measure it, right? But I don't know. In general, there is always a dispersion relation. It depends on the media. What is this dispersion relation? The wave vector, it tells me how fast I'm propagating in a specific direction. Okay? Now my propagation, my speed of propagation depends on the media that I'm propagating, and it also depends on my frequency. Okay? There are some specific medias that it will be proportional to the omega. There are different, it depends on the media itself, okay? And on the direction. So I know that there is some sort of a dispersion relation. Why I built this vector in the first place? Because I know somebody should tell me what is the dispersion relation of the media that I want to treat. Now, assuming that I know this dispersion relation, okay, I know how to calculate not the density of states, but the total number of states that have wave vectors less than k of omega, right? Because for each k, this is satisfied, right? There is a specific nx, there is specific ny, there is specific nz, okay? Now, I'm saying I want to look what is the number of states, okay, that have k vector that is less than some specific k omega. So I want to calculate all the nx squared plus nny squared plus nz squared to the power 1/2 that is smaller than the volume of the system to the power 1/3 divided by pi multiplied by k of omega. All those different n's that satisfy this relation are the different number of states that is inside the system, okay? So the different number of half waves that somehow managed to be squeezed inside this L. Okay? How many of them? Well, count. Okay. This is easy because this is only, I need only to count something, right? I need only to count the total number of integer nx and y and nz. Now, how I exactly count? What is the total number that I have inside over here? So let's look on a one-dimensional case, right? In a one-dimensional case, let's assume that I have only an x. So I calculate what? I calculate this is nx, this is 1, okay? This is nx. This is 2, this is 3, this is 4. I continue this counting procedure till I reach specific size. What is this specific size? It is v volume to the 1/3 k of omega, right, divided by pi, okay, and that's it. So the total number of states in a one-dimensional case is what? Is the length of the line that starts from 0, okay, and ends up with this maximal criteria on the right-hand side. Okay. Now, if I had a two-dimensional case, so I can plot nx, and I can plot ny, okay, and all the different states are such that all those n's are integers. 1, 1, minus 1, minus 1, minus 2, minus 3, 2, 3, 4, 5, etc., etc. So I plot all the different states as points in my two-dimensional space, right? I have many, many points. And I'm asking what is the number of points that are satisfying the relation that is written on this size. What I have to do in order to count all of them? Yes, I have to take a circle of what radius? Of a radius, the volume to the power 1/3 divided by pi multiplied by k of omega, right? So this is my radius. And I count, instead of length of the one-dimensional case, I count the area of a two-dimensional circle. Now this is still not enough. Why it's not enough? Because I don't care about the cases where nx is negative or ny is negative. Okay? So the only thing that matters is this quadrant over here. Okay? So the total number of points that are getting inside a quarter of my circle is the number of states that I will have. Okay? In 1 dimension is a line. In 2 dimension is an area. In 3 dimension, what it's going to be? A volume. Right? Sorry? No? So the number of states, what is the volume of a ball? What is the volume of a ball? Do you remember? What is the volume of the ball? 4 pi over 3 r to the power of 3. What is our radius? What is the radius of our ball? This is the radius, right? We're counting all the number of states that are not too far from the origin. By how much not too far? But exactly this radius over here. Okay? So it is the volume, the power 1/3, divided by pi, k of omega, to what power? 3. Great. We need all the volume of the ball? No, not quarter. 1/8, right. 1/8. The full line over here, 1/4 and 1/8. Why? Because we only need positive n x's, positive n y's, and positive n z's. Okay? This is the total number of states up to frequency omega. Right? We counted all of them. All the different, what is a state over here? A state is an existence of a standing wave. So I have counted over here all the number of different standing waves that are possible inside of box. Okay, when I'm counting up to frequencies up to omega. Now if I want to compute d of omega, okay, the density of states, what do? I take a derivative, right? The density is by how much this number is growing with omega. Okay? So the total number is this number minus this number. Okay? The density is always a derivative of the total mass with respect to the parameter. My parameter here is omega. Okay? So d omega of d omega, it is d to d omega of this guy that's written over here. So we have pi divided by 6, the volume to the power 1/3, divided by pi, k of omega to the power 3. So what is the derivative over here? So pi over 6 we can live, right, with this. So it's pi over 6. Okay. What we have also inside is v, right? We have p pi to the power 3. Okay. And we have d to the d omega of k of omega to the power 3. Do everything understand why it's the density? If I have calculated the total number, why the derivative of the total number is the density? Do I need to explain it? Quiet. Okay, fine. So we have here v divided by 6 pi 2 squared multiplied by 2 k squared of omega dk of omega to d omega. Right? Have I missed something? What?
I think it's 3.
3? Where 3?
Instead of 2.
Oh, here? 3, right. Yes, thank you. D. Oh, d omega here? And there. Okay, yeah, you're right. D omega, d omega. Yep.
The way that
בעברית אם אתה רוצה. Okay.
It must be integer as well.
Well, what we see over here, it has to be integer.
It has to be an integer.
It has to be an integer.
How do we...
Well, you know that not every k is possible. That's the only thing that you know.
Okay.
Okay? Because you start from a discretized space, right? You're saying the only lambda that I can have inside is the lambda that is exactly integer numbers of lambda divided by 2 is entering inside this interval. So you're starting from a discretized situation. Okay, so 3 and 6 here going away, so we have v divided by 2 pi squared, so d of omega equals to v divided by 2 pi squared, k squared of omega, dk of omega, d omega. So in order to compute for the case of the waves the density of states, somebody have to tell me what is the dispersion relation. The moment that I know that what is the dispersion relation, I can plug it in inside this formula, and I have the density of state. Right? So the situation for the waves is quite simple. Okay, so the moment that we know that this is the situation for the waves, we are in a position that we can start to treat the Debye model. Okay? So this is a general formula. We're going to use it in specific cases. We are going to use it in the Debye model, okay, that we will start developing right now, and afterwards in a black-body radiation model. Okay? So any situation where we have a description in terms of waves, okay, we can use statistical physics for the waves, because the energies, okay, are different energies is simply h bar omegas, okay, and the different for each omega we know what is the density of state, right? So any situation where we have waves involved, this formula is going to pop up, and we will see it at least 2 or 3 times during this class. Okay? We have proven it. Now, why I need it? I already told you that we are going to try and understand a little bit more what happens in solids. Right? Now, in solids, we have seen this Einstein model, and we are going to do a little bit better than Einstein. Okay? So we are going to do what is called a Debye model. Something 1913 or 14, something like that. So if the Einstein model was 1908, this was several years afterwards, after they discovered that it does not work. Okay? Now the idea is exactly the same. We have atoms, okay? Those atoms are somehow connected to each other, okay? They jiggle a little bit. We have plenty of them. In total, n atoms. N is a big number. But Professor Debye tells us, well, no, you must not assume that they are all independent. So this is atom. Atom can jiggle in the x direction, the y direction, the z direction, okay? But we cannot assume that the motions of this guy and the motions of that guy are completely independent. This is what Einstein was assuming. Right? The simplest case, we're starting from an independent situation. Debye tells you, well, maybe they're independent. I don't know. Let's show it. So it's a little bit of a mathematical approach. Mathematicians don't usually jump into conclusions. Let's write everything down, okay, and see what happens. Okay? Now here, from a physicist's point of view, we do know now at least that they are all correlated somehow, so we cannot simply assume that all those different particles are independent. Okay? So we also must start with this assumption of Debye. Let's write down everything. Let's write down our Hamiltonian of the system and see if they are indeed independent, yes or no. If they are independent, then there is something critical wrong with this model. Okay? But if they are dependent and we somehow still solve it, maybe those minimal assumptions are sufficient in order to describe what happens on the low temperatures. We do not include the quantum mechanical stuff inside. The only quantum mechanical that we are going to include is in the same way as Einstein included. You will see. So let's look on this model from a classical perspective. We have n particles. They are all somehow interacting with each other, right? And we want to solve this problem. What do I mean by solving this problem? Let's write a Hamiltonian. Okay? Classical Hamiltonian, and afterwards we will see where we are going from this classical description. Okay, so our classical Hamiltonian looks like this. Yep, no. So we have x, I, and j's is position, okay, of particle number I. I is the number of particle. J can be 1, 2, or 3. So it can be the position of the particle in the x direction, in the y direction, or in the z direction. Okay, so it's 1, 2, or 3. Okay, x hat, y hat, or z hat. Now, when I write the Hamiltonian of the system, the first term is the kinetic energy, right? So first of all, I'm assuming that all those different atoms are identical, in mass at least. Okay? So it's 1/2 a sum over all the different i's and all the different j's of 1/2 m x I j dot squared. This is the kinetic energy. Okay? What else I need to in order to write the Hamiltonian? You've done it last year. What's the other part? Potential energy, sure. So here I have a general potential energy which can be very, very, very long, okay, which will include the position of all the different particles. Okay, so I have here u of x11, x12, x13, x21, x22, etc., etc., etc. And it's an extremely ugly and lengthy potential energy. Okay. Now, I don't want to count all the different i's and all the different j's, so I'm simply saying let's forget about this counting over I and j. Let's count over x tilde I, okay? And it's simply degree of freedom. Okay, so I'm not now looking on the different particles. I'm looking the degree of particle number I, number 1, I'm going to call it 1. Okay? The position of the particle 1 in the second dimension, I'm going to term it 2. The position of particle 1 in the third dimension, I'm going to term 3. The position of the second particle in the first dimension is going to name 4. Okay? So I don't want to say this is particle 1 moving in the x or in the y. I'm looking on degrees of freedom. Okay, and I have exactly 3n of them. Okay, so the kinetic energy is simply something like that. 1/2 m. Okay, this is the kinetic energy. And I still have this lengthy form of x1 tilde, x2 tilde, till x3n tilde. Okay? I'm simply counting not particles now, but degrees of freedom. Okay, I want to write it down in a matrix form or a vector form. This is simply, I don't like sums, right? I want to multiply here everything by everything. So first of all, I notice that this guy has a minima at some different x zeros, right? So I know there is a minima of u at x10, x20, x tilde, x3, 0, x3n, 0. Okay? Why I need a minima? I am assuming that there is a minima, because what physicists usually do, they assume that everything is some sort of an oscillator, and if it's not an oscillator, we assume that there is a minima, and we expand everything around the minima of this potential energy. And this is exactly what I'm going to do. I have a general potential energy. I'm assuming that there is a general minima of this potential, okay? And eventually, I'm going to expand my potential energy around this minima. Okay, so I'm changing again my coordinates, and I'm saying, well, xi tilde plus xi tilde equals xi 0 tilde plus xi of I. Okay. Why I do need that? Because the moment I write this in the following term, I'm saying that my Hamiltonian is 1/2 m. I can build a vector out of those guys. Okay, so a vector is psi1, zeta 2, zeta 3, zeta 3n, לבריאות. Okay, so the kinetic energy is simply this guy multiplied by this guy transpose, right? And I have a scalar multiplication between two lengthy vectors. Okay? This is the kinetic energy, right? Because the only dot, right? So what I'm getting out of this multiplication, zeta 1 dot squared, zeta 2 dot squared, zeta 3 dot squared, etc., but I prefer to write it down in this vector notation. What else do I have? I can write down this potential energy over there also as some sort of multiplications between the vectors. Why? Because I'm saying, well, I'm going to expand U around its minima. Okay? So around its minima, the expansion is always going to produce, okay, a quadratic form. So this guy, it's U0, it's a constant, right, plus a second order expansion. The first order expansion disappears. I don't have linear terms because I'm expanding around the minima. I only have second order expansion. So write it down as zeta vector, a matrix A, zeta vector transpose. What is this matrix A? Aij are simply 1/2 du d zeta I d zeta j. Okay? So instead of writing my Hamiltonian in some sort of a not linear but scalar form that I have over here, I'm saying, well, I have here vectors and matrices, okay? And if I would take this long vector, multiply it by its transpose, it's going to produce a sum that it's written over there. If I'm going to take a matrix, multiply it by a vector, and then multiply it again by a vector, I'm going to get a scalar, which is exactly the expansion of U, right? Because when I'm expanding U, I will have U0 plus a derivative of U with respect to x1 multiplied by the derivative of U with respect to x2, and all the different mixtures of all my positions or all my degrees of freedom. Okay? This is a much nicer way to write my Hamiltonian. Okay. Why it's nicer? What I'm going to do now. So here the problem is in this form over here. I have a lot of different mixtures that are located in this form. So I can have here zeta 1, zeta 2, du d zeta 1, d zeta 2. Okay? Terms like that, they are mixed terms. I don't want them. Okay? Why I don't want them? Because eventually I want what I'm trying to get. I'm trying to get to a representation that my energy is a sum of energies of independent particles. Now it's not a sum of energies of independent particles. So the kinetic energy is a sum of energies of independent particles, but the potential energy is not. Even when I have expanded it, using a Taylor expansion, it still have mixed terms. It depends on the multiplication of zeta 1 and zeta 2, and zeta 3 and zeta 4, etc., etc., etc. I cannot say that the energy is the energy that's associated with zeta 1 plus the energy associated with zeta 2. There is a mixed term of association between the first and the second degree of freedom, and the fourth and the seventh degree of freedom. They are all correlated. This is how we started over here. And this is the main problem. This is where the bias says, this is where you're wrong, Professor Einstein, because they're all correlated. What can we do in order to get rid out of this? Okay? What do you do when you have a set of equations of correlated variables? And especially, what do you do if you have a quadratic form? Okay? This is in mathematics, it's called a quadratic form. But it's not exactly separable, this quadratic form. What I need to achieve in order to describe all of this eventually as a sum of different degrees of freedom. I want to change my coordinates once again, okay, such that those terms over here will become okay, independent of each other. So I want to change to new coordinates where I won't have multiplications of zeta 1, zeta 2. I will only have zeta 1 squared, d squared u, d zeta 1 squared, plus zeta 2 squared, d squared u, d zeta 2 squared, plus etc., etc., etc. I want coordinates where only all those terms survive. All the other terms I have to get rid of. Okay? But they're there. Because u's are all the different possible derivatives of u with respect to the mixed zeta 1 and zeta 2, or zeta I and zeta j. So what do? I change variables, or more specifically, I need to diagonalize somehow this matrix over here. Because if this matrix A was a diagonal matrix, right? What will happen if it's been a diagonal matrix? So assume that I have 1 and 1 multiplied by 1, 1, 0, 0, okay? Or zeta 1, zeta 2, and I will have here zeta 1 and zeta 2. If I multiply this guy by a diagonal matrix, and again by a transpose of the same vector, I will get a sum of zeta 1 squared plus zeta 2 squared. This is where I want to go. In the current situation, A is not diagonal. This is why my Hamiltonian is a bad Hamiltonian for me. Okay? It's not a sum of independent something. It's a sum of mixed something. So my next step is the following. I want to change variables such that, okay, all this form will be a simple form without mixed terms. This is what I want to achieve. Okay, we have 15 minutes to do this. Yes?
But if you change your matrix, don't you also have to change the representation of...
Exactly. I need to change everything somehow such that I will have a different form, okay, of independent variables.
Right.
You're completely right.
Right, but these zetas describe your system as this.
Yes.
If you change it, then it won't describe... It will describe the same systems, but in different terms.
But this is the point, you see? What I'm saying is I cannot describe my system using the x's or the zetas and get an independent representation. I can't. This proves that I cannot because my A is not diagonal. Okay? Now I'm saying, but maybe if I will stand on my head and I push my hand to the left and to the right, I will see the system in different terms such that in those terms they are all independent. I'm not saying that I'm going to describe it as those positions of those particles. I'm saying that there is a representation of the system in different terms where they're all independent. This is what I'm trying to do. And this is exactly the point, okay? The point of statistical mechanics here is not saying, well, it's a complex problem, let's treat all those correlations. The only way we know how to treat correlation is to use different representations. What you have been trying to achieve in classical mechanics, okay? This Hamilton-Jacobi equations. What is the point of Hamiltonian prescription? Eventually, the point to present everything in different geometry where all the particles are either free particles or harmonic oscillators. This is what we've been trying to do. Exactly this is what we are trying to do here. This is unsolvable in those coordinates. Maybe there are other coordinates where this energy, because Hamiltonian is an energy, is simply a sum. Simple sum without mixed states. Okay? Okay, so where we're going in the following states. So A, I'm going to write A, and it's a general theorem. I can write A as a multiplication of D, S, and S minus 1. Okay, I can say the following. What is A? D, it's a diagonal matrix. And S is the matrix composed of eigenvectors of A. I assure you that you once learned this theorem, that every matrix A that has, if you know its eigenvectors, you can use this representation, okay, for this matrix. It was during your first year, whoever taught you that, but you once learned this theorem. Okay. The moment I'm going to use this S and D in order to represent A, I can write down my Hamiltonian slightly differently. So let's look on the kinetic term. So here we have Hamiltonian equals 1/2 m zeta vector dot, right? Here we have zeta vector dot transpose, okay? Here we have zeta. Here we have S, right? D S minus 1. This is the representation of matrix A. I don't tell you what D is, but there is a matrix D. This is a theorem. Multiplied by zeta transpose. Okay? And there is some additive constant V0, U0. We don't really care about it. Okay. Now, instead of simply multiplying those two vectors, I can put here S and S minus 1. Right? Because S is a matrix composed of the eigenvectors of A, S minus 1. It is an inverse matrix. S multiplied by S minus 1 is the identity matrix. So everything is fine over here. Okay. So let's continue. So we have 1/2 m zeta dot S, S minus 1 zeta dot transpose plus, now look on this guy over here. We can say that it is zeta S multiplied by D, and here we have S minus 1 zeta transpose. S minus 1, okay, it's composed of the eigenvectors, okay, so we can simply say that it is an S transpose zeta transpose. Okay. Why is that? Because we use this fact that S is composed of eigenvectors of A. Okay. What is the next step? The next step is to say that here S minus 1, we're also going to use this trick of terming it a transpose. Okay? So it's 1/2 m zeta s, all of this dot, right? Here we have S transpose zeta vector t, all of this dot, right? So this is already a vector. This is also a vector, okay? But this is a vector of my new coordinates, plus what I have over here. Again, this vector of zeta s, okay? The same as I was using it over here. Zeta s, a diagonal matrix. Remember, this is what I was hoping for. A diagonal matrix D. And here, okay, I have a zeta s transpose. Yes? I think so. Now we're changing again our variables to something different. And we're saying we can have a vector z, which is z1, z2, up to z to the 3n. And what is z equals to? Z equals to zeta multiplied by this s over here. Okay? Now, if I want to write my Hamiltonian in terms of, instead of zetas, in terms of z, what I have, then my Hamiltonian is 1/2 m z dot transpose plus z d z transpose plus some u0 that I don't care about. Now, what is this guy? This is 1/2, or write it down, a sum I from 1 to n, 1/2 m z I dot squared plus a sum from 1 to 3n of what? Here is a diagonal matrix. So it's d I, okay, zi squared. So we got a Hamiltonian, which is a sum, a simple sum right now, over 3n different variables, which are completely independent of each other, okay? And the energy of each variable is 1/2 zi dot squared plus dii zi squared. Now, what is this? Energy represents. This is an energy of a harmonic oscillator. Okay? So what we have managed to prove? We have managed to prove that we started with a correlated system. If we expand the energy, which can be very, very, very complex, but we still expand it, okay? We can find a representation. I haven't told you what is exactly this representation, but we can still find a representation, okay, in terms of z's, such that each degree of freedom behaves as a harmonic oscillator. Okay? You're saying, well, yes, now you can go back to Einstein model and say, just use these d's over here and z's, and that's it, and forget about everything else. So, dear Deba, you have proven that it can be done, but still, Einstein does not work. Why it won't work? Because it's not enough to go here and say, well, now I have an Einstein model. Why it's not enough? It's exactly because of what you say. I don't know what those z's are. Z's are not positions, right? Z's are some degrees of freedom, something that oscillates inside the media. Okay? what kind of solutions produces harmonic oscillator, sinuses or cosinuses that do not decay as a function of time. What is a sinus or cosinus that is not decaying as a function of time? It's a wave, standing wave. Okay? So the next step of Debye, that is, he is saying, I'm not using the coordinates of the atoms, I'm using some generalized coordinates, and those coordinates produce sines and cosines. They're producing waves. So I'm trying to describe everything inside a system in terms of waves that are given me by those harmonic oscillators over here. Okay, this is a crucial step. I cannot simply say, well, I have a sum of harmonic oscillators. I'm saying I have a sum of waves, of standing waves. Instead of particles, and this is actually natural. Why? Instead of particles, I have a huge combinations. You see this guy. I don't know exactly what Z is. It can be position of particle number 1, the Y position of particle number 27, and the Z position of particle number 3 multiplied by -1. I don't really know what this coordinate is. I only know that it produces waves. And I need now, in order to finalize this computation, this description, I need to use the wave description for this solid. And this is what we are going to do on Tuesday. Thanks.